Morning, everyone. So continuing with our review, I just want to give you a few quick highlights from our wave optics section. For starters, let's just define a wave again. The function of a wave here is to actually transfer energy. So wave function is to transfer energy without permanent displacement. So unlike objects that are actually passed from place to place, where particles need to physically move from one side to the other, a wave is this disturbance or this message that can be passed along. If you imagine a Slinky analogy here, let's start off with the Slinky that's just being held between two fixed ends here. You can refer to those ends there as nodes. Basically what you can do to the Slinky here is you can start rocking these Slinkies back and forth. As I just sort of send a pulse down, basically we can do a quick little up-down motion here, and what's going to happen is it's going to end up creating a pulse that actually travels along the wave as well. In this case here, the wave is moving left and right, although if you tag any particular particle along the Slinky, you're going to actually realize the particles themselves are just rocking up and down. So that's the goal of a wave here. We first categorize our waves into two main types. I'm going to start off just reviewing with you. First type here is called an electromagnetic wave. Pretty much this is our example of light. So electromagnetic wave here, these ones here do not require a medium to travel. So that word medium just refers to a background material. So there has to be actually particles that is traveling through. In this case, the electromagnetic wave doesn't care for this medium. Right? It can just travel through the nothingness of space. In science, we refer to it as a vacuum. So as we look at light, we have what's referred to as electromagnetic spectrum. We learn that the visible portion of the spectrum is actually a really narrow range. So we have our Roy G bit of colors, red, orange, I don't have orange, so yellow, green, blue. Our rainbows are always in this order because these are actually the ordering of our wavelengths. So I'm going to just roughly plop down. The red side is the roughly 700 nanometer side. I'll recap that definition with you in a second here. The purple end here is the 400 side. Yes, 399 would still be purple, 750 would probably still be red, but roughly you can ballpark it this way. We have some forms of light that are more energetic than visible. So let's go into the UV, the ultraviolet. Ultraviolet means you're going beyond the violet end. So that's the typically from the sun. You're worried about these UV radiation. That's more energetic light. We have X-rays, which can go through soft tissue, no problem. It reflects off your bones like a mirror, and basically it can be a nice imaging of your skeletal structure. If you go really high energy here, we have what are referred to as gamma rays. Gamma rays here, sometimes they just use the symbol gamma for it. Okay, in that case, those forms of light are more energetic than light. There are some forms that are less energetic as well. If we go into the red, we are infrared. It always looks like infrared to me. So infrared, I can say IR radiation here. As you get lower and lower energy, we get into those microwaves, really sensitive to our water molecules. So if you picture like a water molecule here, covalent bonds here act a little bit like springs. They're constantly sort of stretching and contracting. The angles are being squished here. Microwaves are perfectly the right amount of energy to cause the water molecules to start vibrating and moving around a little bit quicker, and that amounts overall macroscopically to be a slightly warmer plate of food. And then we get into our radio waves here. We know when we turn on the radio waves, suddenly you can hear the broadcast. The radio waves are constantly around us, but without a device that's sensitive to that regional electromagnetic spectrum, it's completely invisible to us. Right? What's important for us to know here for this spectrum here, all of these waves, all light travels at c, which is 3.0 times 10 to the 8. That's referred to as the speed of light. That's the speed of light in vacuum. So I don't care if you are a low energetic wave like a radio wave or really energetic like gamma, they all travel speed-wise, always the same. So that's going to be a constant. However, we've been saying, well, these are different in terms of how much energy they carry. Based on the way I've sketched it, going from radio to gamma, we actually have steadily higher energies, although the speed of the wave is essentially the same. We had two formulas. One formula here, actually the second formula that we got with was the fact that energy is proportional to frequency. So we have through the Planck Equation, Planck equation says the energy of a light particle, we refer to a light particle as a photon. Light is not matter. It doesn't have material. It's little packets of energy that are actually passing from one place to the other. It's actually proportional through frequency. So therefore, the higher the energy side here, we actually have higher frequencies as well. That's going to amount to if I'm on a metaphorical boat here, as the waves just by me, I'm going to go through many up and down oscillations, full motions for every second. That one there is referred to as frequency. We have what's referred to as the universal wave equation. The universal wave equation says the speed is the product between frequency and lambda. Lambda is wavelength. Basically, because the speed has to stay constant, for light it has to be 3 times 10 to the 8. For water waves, the speed may be a little bit different. The speed of sound is about 300 meters per second, so it's a little bit different. But basically, the speed has to be some constant in that particular medium, and it gives us an opposite relationship. As the frequency goes up, for me to multiply to give the same number, the wavelength has to shrink. So therefore, just based on this generalization here, going in the direction that we've just listed down, as I point towards the high energy, that's definitely the more frequent end, higher frequency, we also have the shorter wavelength end as well. So the shorter the wavelength, the higher the energy that's passed from object to object. Right? So let me just qualify some of these terms again. We're going to imagine we take a still photograph of a wave. Wave demonstrates for us what's referred to as periodic motion. Periodic motion is a motion that repeats, right? It's periodic. So this is a still frame, right? X is horizontal, Y is vertical. Instead of really taking a picture of the length of the wave, like how long the wave actually stretches out, because it's periodic and because it repeats in little cycles here, I'm just going to find how long until there's a repeat. So, for example, I start off here. It's a very sinusoidal shape here. It goes up, down, and then back upwards. That one there is one cycle. It's one sort of unit. And if I copy and paste that particular unit, I basically get all the other parts of the wave. So when I refer to wavelength, I'm actually referring to basically the length before it repeats. Just for simplicity's sake, we just refer to, well, the tops here, we know these are called crests, right? Those are the peaks of the waves. They're the maxima. We have the troughs, which are the minima, which are the lowest points on the waves here. And basically, just for simplicity, we say, well, wavelength is the distance between one crest and another crest here. So this one here, wavelength. Wavelength is a length, so it's measured in meters here. It's the distance between crest to crest. Right? It's from the really top to the really top. Imagining if I was on the top of this and I was looking downwards, we can actually look down at this wave tank here, and I can actually see bands of dark and light. And essentially, if I'm looking downwards here, we refer to these as wave fronts. You can track these either or. You can say wave fronts is a line of all the crests. So if I imagine I'm sort of above, my eye is sort of looking down on this tank here. If I just draw a line for all the crests all at once, they're going to actually line up for this rectangular wave here. So those mark off the crests here, the distance between one and the other. On this picture here, then the wavelength here is just the distance between peak and peak. Right? So crest to crest there. We have a couple of other readings here of, let's say, amplitude. Amplitude is going from the no wave line. The no wave we usually refer to as the rest line or the equilibrium EQM line. The amplitude is actually the maximum distance, how far the crest gets away from the rest line, how far does the trough get away from from the rest line here. Amplitude is always a positive number, and amplitude here is actually some measure of how much energy it carries. There's actually two ways that we can see the energy carried by the wave. One is through the amplitude. So I can have a wave that has a much larger up and down motion, much larger peaks and troughs. And basically, in the sound analogy, that amounts to volume. So if you crank up the volume, basically the pitch is the same. The wavelength and everything looks identical, but you're just sort of giving it a little bit more intensity. The larger the peak here, it's a louder sound. In the light analogy, that amounts to a brighter light. We can also change the frequency, so we can change the pitch, change the tone of it by changing the frequency. Instead of rocking your hand up and down and making these slinky motions here fairly slowly, I can oscillate my hand up and down much quicker, and basically what that would amount to is these waves here will be a lot closer together. In that case there, that would be also carrying a lot more energy. In the sound analogy, it would be a higher pitch sound. In the light analogy, it actually turned to a higher energy color. So when we listed earlier here, we were saying, well, red wavelength here is roughly like 700 nanometers. I want to remind you that light, our little packets here, light just travels in a straight line. It doesn't actually oscillate up and down. The things that are rocking up and down metaphorically are actually light waves and magnetic waves. If you go on to physics, you're going to see a little bit more of that. But pretend this red stream of photons here is just coming straight at you, but just to represent the energy carried by those photons, I can have these waves here sort of oscillating back and forth. Compare the red light wave here to a purple light wave. A purple light wave here has a shorter wavelength. It's a high energy wavelength. Its wave peaks will actually oscillate up and down a lot quicker. Again, the purple photon also zips by you. It just goes straight. It doesn't actually rock back and forth. It doesn't zigzag like that. But you see that the wavelength here is actually a little bit more narrow. Now to link it back to frequency then, if you imagine you are sitting on a boat, metaphorically as this wave here rocks up and down, a little bit later, this wave here would have pushed a little bit by you. You're going to rock up with the wave. The wave is going to keep pushing past you. You're going to start rocking down with the wave here. You're going to count how many times you oscillate up and down as a full motion, and that's referred to as a period. So in this case here, the time for one full rocking up and down motion, that's referred to as a period, because that one there is a time. It's measured in seconds. Frequency is the opposite of that. Frequency says, I don't have all day. I don't want you to wait an infinite amount of time. Maybe it takes a minute for a whole wave to pass by. What if I just give you 1 second of time? I just give you just a split second, 1, 2, 3. Just with that 1 second of time, tell me how many full cycles do you get per 1 second? In that case there, we can refer to this as a frequency. And these ones, as we've seen, are sort of reciprocals of each other here. Frequency, you can use the letter F. Sometimes you use the Greek letter nu for it. It's like a V with a little bit of a squiggle. And this one here is in per second. The unit for that one there we can actually use is hertz, Hz. Right? Let's just practice a quick example there. Let's actually go to a much longer wavelength because we haven't used this yet. So let's say we have a microwave. Those waves that the water particles are really sensitive to, as they dance around faster, it's going to amount to a hotter substance. Let's say I take a wavelength, microwave here has a wavelength of 50 centimeters. Right? I want you to calculate for me using these equations. Can you calculate for me the frequency? Can you calculate for me the period? And calculate for me the energy of this microwave. Now I know on the electromagnetic spectrum we're at the really low end. I'm not expecting it to carry a lot of energy, but still we can calculate it. So the first thing you want to do here is you want to convert everything back into SI units. Even though I know this time the wavelength itself is actually 50 centimeters. It's actually quite sizable in comparison to the nanometers that we've been working with so far. We still need to convert it to a meter. So 50 centimeters here is actually 0.50 meters. Let's have a look at our equations here. Even though microwaves here are fairly low energy, they are still on the electromagnetic spectrum, so we can still use the universal wave equation. C is equal to lambda times F. The speed of light is still going to be 3.0 times 10 to the 8 meter per second. Now that I have lambda in meters, 0.50 meters, I can solve my way through for frequency. The frequency is equal to 3e8 divided by 0.5. This gives me here 6.0. times 10 to the 8. The units here is going to be per seconds, or you can just use hertz for it. This part here means if you give me one whole cycle of time, I actually travel 600 million up and down motions for every second that passes by. Why is this one here, each second? Why is this one here still so ridiculous here? Even though the 50 centimeters here is much, much larger in comparison, like we said for the nanometers, it's just because light travels so ridiculously fast. This whole wave zips by you super quickly. So if you are metaphorically on this boat here, as it rocks past you, it pushes by you a little bit here, you're going to go upwards, it keeps pushing past you, you start falling downwards, you're going to rock up and down here. You're going to do that 600 million times in a second. That's just putting in context how quick this light particle is actually traveling past you. Let's calculate the period here. Period, we're going to use T for it. The period is the reciprocal frequency, so we're just going to go 1 over this frequency here. When I take the 1 over here, 1 over 6 times 10 to the 8, This one here, 1 over our answer gives me 1.7 times 10 to the negative 9. This one here is now going to be seconds. So if in 1 whole second you travel this 600 million times, if you just give me 1 cycle worth of time, I would imagine this is only it's kind of a fraction of a second. It doesn't take that long for just one up and down motion. With the frequency, we can also, using the Planck equation, we can actually do E is equal to hf. H is Planck's constant, so 6.63 times 10 to the negative 34, all on your formula sheet, so you don't need to memorize it. You just need to know how to plug that number in there. And basically, if I take that 600 million oscillations up and down every second, I rescale it through Planck's constant. This will give me my energy in joules. So I'm getting 3.98 times 10 to the negative 5, so let's go 4.0 times 10 to the negative 25 joules. Right? It's not a very energetic form of electromagnetic light, so I expect the energy to be a little low, but again, this is just the energy for one single radio particle. What if I have a whole stream of radio particles here? This energy here can stack up really, really quickly. The next thing what we did here is, as we started looking more at this wave introduction here, is we started looking at how waves actually interact through different media. So let's start off here. Let's say we have air as a medium. Air has what's referred to as index of refraction. The index of refraction is 1.00. Let's say this light wave actually travels from air into water. Water here actually has an n value of 1.33. Those would typically be given to you. We're going to start off here just dealing with the refraction case. So as light is trying to cut its way through air, what we're going to see is the frequency is actually set by the source. So let's say it's the sun that's actually giving me this light source here. Whatever frequency, whatever up and down oscillation that the sun gives me for starters, it sort of sets the beat that the marching band has as it travels through. Because light is an electromagnetic wave, it doesn't actually need a medium to travel through. It doesn't mean that it can't travel through. So in this case here, it's traveling through air, no problem here. We can actually, using this index of refraction, that's what this N stands for. Using this index of refraction, or refractive index, we can actually get a feel of how the speed itself actually changes. One way of looking at it here is just going, well, C, the speed of light in vacuum, is going to be the velocity of light here in my new medium. Basically, this N here ends up scaling down the speed a little bit. So if I just use that formula here, essentially the C stays constant. In vacuum, always 3 times 10 to the 8. In our relativity section, we saw that represented a maximum speed. You can't actually go beyond that speed. Things start getting really messy, masses increases, time slows down, things get really, really strange. Now, what's my velocity, let's say in air? Well, because air's refractive index, it's sort of like an optical density. Because air is practically going to be 1, the speed is not going to change by much in the air. However, if I try to do that in water, let's do the same equation. Well, the vacuum doesn't change, but the speed in water, because my index is now a little bit higher, it's 1.33, I need to take 3e8 divided by 1.33. This ends up giving you your velocity of water actually is less, still ridiculously fast, 2.3 times 10 to the 8. So if you imagine a sort of marching band analogy here, as the marching band heads towards this water surface, the frequency is set by the source. I want to keep emphasizing that. Frequency depends on the source. Sort of the beat that this marching band has is always going to be constant. Even as it enters into a medium that's more dense, the beat is still the same. It's just going to be a little bit harder to travel through here, so they're going to end up slowing down. Remember, for this stuff here, we typically measure our angles relative to the normal. So pretend that our water surface is perpendicular here, so therefore our normal is straight up and down. In this case here, I'm going 0 degrees relative to the normal, so therefore, even as I enter, the entire marching band, all the marching band people, they run through the surface, they all slow down at the same pace, and we did a few problems for there. As we just sort of work out that marching band analogy, we get into Snell's law. What if we actually send in this light wave here along an angle? So light can be thought of as either a ray or a wave. So as a ray, you can think of it as a stream of photons here. We measure the angle. This is called the angle of incidence. It's the angle that it's coming in. This ray here is called the incident angle, or incident ray. So it's entering here. Basically, as we go from a lighter dense medium to a more optically dense medium here, we're going to see that this ray here ends up bending towards the normal, and it's going to end up refracting. Refracting means goes through. For the refraction, we actually bend towards the normal, going from an easy medium to a hard medium, going from a small n to a hard medium. So this is going to be theta 2. This is, remember, where our brain plays tricks on us here. Our brains always interpret, oh, it's light. It travels in straight lines here. Even though the fish, the light that's reflecting on the fish here might actually bend as it goes through the surface here, our brain interprets, oh, that means our fish is actually just straight across here. We've produced what's called a virtual image. These are not real light rays. The fish is not really there. We sort of forget about the fact that light actually bends going through the surface here. So using that marching band analogy, again, the frequency is set by the source, but if you've ever seen a marching band here actually slow down, what ends up happening is one side of the marching band actually runs into the surface first. Those particles end up slowing down. Little do they know, the other side here doesn't see it yet. The other side here just continues forwards. Basically, we're going to steadily get, well, this side of the marching band had to slow down. The other people don't know yet. Still, people don't know yet, but more and more people start knowing. And basically, this is how your marching band ends up turning. Again, it's going to overall be slow. The frequency is set by the source, but because the velocity is less in the air, it ends up bending towards the normal. Just before we get into reviewing Snell's law here, there is another way for you to start thinking about this optical density. I don't know if I mentioned when we actually did the lessons here. What you can think about here is for these indices of refraction, or refractive indices, that's just plural for index. Refractive indices actually describe a ratio of velocities in different media. So just another way of thinking about it here. Doesn't really change anything else. So different media is plural for medium. So imagine with me here, what I want to do is I want to just figure out what's my velocity in water as compared to the velocity in air, just for argument's sake here. Well, since these ones here are velocities, I can use the universal wave equation. The universal wave equation says c is equal to f lambda. Remember, c is representing the velocity. This time I'm not traveling through vacuum, so I'm just v. So the velocity in water will be the frequency in water, the lambda in water, all over the frequency in air, the lambda in air. We just said the frequency is set by the source. The frequency, the beat, is set by whoever's generating these waves here. Even though we end up slowing down, even though we even bend towards the normal here, these frequencies are the same. So these ones here actually end up canceling out. So we can actually get already a sense of, well, the ratio between the velocity between two media are going to have some change relative to their wavelength. We're going to use our other formula here. V is equal to C is equal to V over N as well. I'm just going to rearrange that. That means V is equal to C over N. I can also think about this in terms of, well, the velocity of water here would be the speed in vacuum divided by the N for water, divided by the C, divided by the N in air. Here we actually have a fraction over a fraction. Remember, when that happens, it's basically multiplied by the reciprocal. So it's like taking the first one, C over N water, multiplied by the upside down of the N air, divided by C. The speed of light ends up canceling out, and therefore we see that the ratio of my speeds between water and air, sure, it's now the upside down, but basically we have, it's given by the ratio of N air over N water as well. So it's just another way for you to start thinking about it here. N is this optical density. Because every material has different optical densities here, there might be a ratio between different optical densities going from air into water, and that'll amount to not only some difference in wavelength, the color of light may actually change depending on how quickly the speed, the wave can actually pass through, but it also depends on the relative ratio between velocities as well. Right. So let's just move back and just rehash for you Snell's law. So Snell's law here, it gave us a nice connection for both reflection and refraction. And basically it said n1 sine theta 1 has to equal to n2 sine theta 2. Right? for starters here, if we end up doing reflection, our typical optical device that ends up doing reflection is a mirror. Basically what ends up happening is the incident ray here is oncoming to the mirror. It comes in at some angle of incidence. Because for reflection, I end up expecting to stay in the same medium. In this case here, the ends are the same. Those ends are canceled out. You can inverse sine both sides. Theta 1 actually equals to theta r, or theta 2. So in this case here, for a reflection, we actually just bounce off in the same angle as was before. More interestingly here, I'll do it as an example. As we went from, let's say, air into water, we're coming in at an angle, let's come in at an angle of theta I. I'm not sure what that is. Let's say we are in the air, so n is 1.00. Let's say we enter into a different liquid here, just for kicks. It's not water. Let's make it 1.40, right? So slightly more optically dense than water. Let's say this one here, we expect it to bend towards the normal, although our brain tricks us and it thinks it's traveling in straight lines. The real light ray here actually bends closer to the normal. This theta 2, let's say for argument's sake here, theta 2 this time is 15 degrees. So I would expect already theta 1 here should actually be less than 15. Let's try out Snell's law. N1 sine theta 1 equals N2 sine theta 2. 1.00 sine of the unknown is equal to 1.40 sine of 15. Make sure your calculators are in degree mode when you do this. So therefore sine theta 1, 1.4 times sine of 15. This gives me here 0.362, and therefore I inverse sine it. Inverse sine of 0.362 gives me roughly 21 degrees. And as expected, going from an easy medium, something with low optical density, to something that's harder than it, the angle bends towards the normal. They could also frame this a different way here. For this medium, can you determine the critical angle? Essentially, the critical angle, it only applies when we go from a high optically dense medium to a low optically dense medium. That's when we actually bend away from the normal. So imagine flipping this picture around here. Imagine we were underwater. Again, usually we're not Cyclops and we're not actually sending light rays. Light rays are actually going in reverse. But just for simplicity, if I end up looking out here, if I start off in the medium that's hard, 1.40, and I end up going into medium 1.0 that's easier, I should bend away from the normal. The critical angle is such that I bent so far away from the normal, this would have been 0 degrees here, and basically it's bent so far away from the normal that my light ray just happens to coast along the surface. As it coasts along the surface, our theta 2 is equal to 90. Anything bigger than this critical angle ends up reflecting back the way it came. So let's just try out Snell's law again. M1 sine theta 1 and 2 sine theta 2. This time I'm starting in the hard medium, so 1.40 sine of some special angle. As I leave, I enter a medium that's 1.00, and then we have sine of 90, and sine of 90 ends up being 1. So I can go sine of theta c is equal to 1 over 1.4, so 0.714, and therefore my theta c, inverse sine of this one, is 46 degrees. So what that means here is anything beyond 46 degrees for this medium, basically we're bent so far away from the normal. Let's say I decide to look out at 60 degrees, right? I know it wants to leave. It's going to have bent so far away from normal. At 46, it's already just managing to escape. At 60, it's no chance of actually escaping. It's actually just going to reflect because I'm staying in the same medium. Therefore, this angle is just 60 degrees. We call that phenomena here total internal reflection. Even though this surface of the liquid here should be transparent, we should be able to look through it. In this case here, we bent so far away from the normal that we actually reflect back into the solution that we have. Right? Then we actually looked in detail into our optics directly. For optics, we had mirrors and we had lenses. For mirrors, our keyword here is they do reflection. For lenses, we expect the light rays to get through. These ones here do refraction. Make sure you're comfortable drawing the ray diagrams. Just let me hint at these ones here. So ray diagrams, especially for a curved mirror. Let's say the candle is over here. We have a curved mirror. A couple of different definitions for us here. We call the line the principal axis. The point where my mirror intersects, the principal axis here is called the vertex. we're going to imagine a roughly spherical mirror. So this mirror here would have had a center of curvature, the center of a circle somewhere. That's called C. The halfway point is actually called the focus. Focal length is referred to the distance between the vertex and the focus. Right? So for a mirror here, we fully don't expect light to actually be able to travel through. We're going to draw two light rays using a ruler. So parallel light ray is going to focus through there. That's a converging mirror. The other one here, imagine it hits through the center curvature, it hits the mirror and comes back undeviated. Where these two here intersect, end up where the image appears. If the image appears with actual light rays traveling through, we refer to it as a real image. There's an actual light rays actually converge, and in this case here, this can be projected on screen. Right. So if I put a piece of paper here, because the light rays had to sort of converge at this particular distance here, I would see a really nice mirror image, a nice reflection of that candle. It's possible that the mirror can be the opposite way. So let's say this is a convex mirror. A convex mirror here, we actually have a negative focus because our center of curvature is inside the mirror. The focus, which is halfway, it's on the negative side of the mirror. The positive side is the side where the light rays actually stay on. The negative is the opposite side. For my ray diagram, a parallel ray, it ends up diverging, it ends up separating as if it had come through F. A light ray that was on collision course here with the center curvature, again, the real light ray here hits the shininess of the surface and bounces backwards. On this side here, it actually diverges, it actually separates. In this case here, when they intersect, you notice I did these dotted lines here. This is now called a virtual image. Virtual images will always have a negative DI. Right, the DI will be a negative number. If you look at the shininess of the mirror surface, it looks like this image here is physically inside the mirror's world. It's not, oh, let's walk behind the mirror and see where it is. Because that's physically inside the shininess of the surface, I cannot put a screen there, and I can't actually project that. Let's switch over to our lenses then. For lenses, the one that does converging, converge is meaning coming together. It's actually a bi-convex lens. In this case here, similarly, we have a vertex, we have a focus. We usually call it a two-focus point on both sides. In this case here, we're going to have our candle. Let's put ourselves, let's say, in between here. A parallel line here converges through F. The other line here that is undeviated is the one that goes through the vertex, and we can find where the intersection is. Oh, these are real light rays that actually pass by. We actually have a real image. The positive side for a lens is the opposite side, whereas the negative side of the lens is actually on the same side. If I do a biconcave lens, this one here is the divergent case here. Again, we can list our same variables, f and 2f, f and 2f. These really depend on the curvature of the lens itself. In this case here, a parallel ray, it diverges as if it came from F, and the other one here, it goes through the vertex undeviated. Couple things you can describe for the image in addition to being real or virtual, whether I can project it or not project it. In this case here, I can say this image here is still upright. It's still the same orientation. The candle is still standing up tall. I can mention it's diminished. Diminished refers to the size of it, and the size of it has actually shrunken on you. So that's a diminished image here, and we talk about virtual being on the same side of the lens. Right? For both mirrors and lenses here, we use the same equations. Same equation here, 1 over f is equal to 1 over di plus 1 over dou. And the other formula is the magnification, which talks about how do the image heights compare to each other. High over ho equals negative di over dou. Right? So I'm just going to end off this review here, just giving you two worked out problems, one mirror and one lens for you to work with. So first example, I want you to tell me here, an object, a 2 centimeter tall candle is placed 10 centimeters from a convex mirror with focal length 5 centimeters. I want you to calculate a couple things here. Part A, calculate the image distance. By doing that, you would have figured out whether we're real or virtual, and then determine the image image height. Okay. So one quick caution for you here, you can definitely sketch out a ray diagram here. I would list off the variables if we can. So 2 centimeters tall, that's the height of the object. It's placed 10 centimeters. This is physically in front of the mirror, so this is going to be your object distance. Object distance is always positive. Object distance is always positive. Right? Even for a lens where the same size should actually be negative, no, DO should always be positive. But you have to be really careful. In this case here, for a convex mirror, we just said convex does a diverging case. For diverging, that convex means it actually has a negative focus. The focus is actually on the other side of the lens. So even though they just give you by magnitude 5 centimeters, when you punch an F, because convex as a mirror is diverging, we actually want to put in an F of negative 5 centimeters. So look out for that one. I'm going to give you an example of a lens problem here. Let's give you the magnification of an object is 3 times larger and inverted, meaning it's upside down. What I want you to find for me here is if the focus of this lens, you can think about what lens it is. If the focus of this lens is 4 centimeters, I want you to calculate the D naught. Calculate how far from the object I am so that my image is 3 times bigger and it's inverted. I'm specifying in this case, again, I'm just going to give you a few hints here. I'm specifying we're talking a lens, and I'm specifying that the focus is actually 4 centimeters. This focus here could be, if it's actually a positive number, we're talking here a convex lens. Try it out, see if the math works out. Or you can try it here. It's still possible that maybe we're still a concave lens where you actually want to put in a negative. See which one here matches up for your work. You should find that the answer is actually a convex lens. Okay. A little bit of algebra for you to solve here. Let me just hint at that first a little bit. You have the magnification, which is equal to negative di over dou. The magnification, they tell me it's 3 times bigger, so the value is 3. To tell you that's inverted, I actually need to say negative 3. This time here, it seems like we don't have enough information, right? I have this di over dou, but I can just rearrange this expression. So therefore, let's multiply the DO up. Let's get rid of the negatives. The DI is actually going to be 3 times what DO is, right? And in this case here, because we know DO has to be a positive number, therefore the DI also has to be a positive number. For a lens, we have to be on the opposite side of the lens. So for the lens here, we have actually a convex lens. So this one here is correct. My object distance here is always going to be a positive. That's positive DO. We would normally, however, say this is the negative side of the lens. I expect the light rays to actually pass through. We expect the light rays to be positive. The image is actually going to be 3 times as far as the object distance. If that's the object distance, my image where I actually end up intersecting actually ends up on the positive side, and it's actually 3 times what DO is. With that, you can actually punch your way through using the other formula. 1 over F is equal to 1 over di plus 1 over dou. You can try substituting. Instead of this di here, I'm going to actually sub this in as 3 D naught. The F, we now know it's a convex lens, so this has to be 4 centimeters. See if you can work your way through and find what D naught is. Right? So keep practicing through. If you have any questions, just let me know. Thanks, guys.